All right, so we ended the last video with this kind of shortcut approach you can use to figure out a limit at infinity by looking at the degree on top and bottom. Okay? So when you're doing the limit at an infinity of a rational function, a shortcut you can use is just to compare the degrees, and that'll give you a sense of one of these three cases. So let me clean this up a little bit and make sure you understand the basics of the three cases. All right, so you might get a horizontal asymptote, and that horizontal asymptote might wind up being y equals 0. Okay, so that's one case. That's going to happen if you have a situation where the degree was bigger on the bottom. So the bottom grew more rapidly. Okay, got bigger more rapidly than the numerator. So that's the case if you had something like a negative 2x for the leading term on top and a 3x to the third on the bottom. The degree bigger on the bottom means the function on the bottom is growing more rapidly than the numerator. So that is going to wind up having a horizontal asymptote at y equals 0. Okay. Then if you have a situation where the degree on top and bottom is the same, like on the example we did, number 5b, then what this is saying is you will have a horizontal asymptote, but it won't be equal to 0. It'll be equal to some number that can be found by just taking the ratio of the leading coefficients. The reason that's the case is the function on top and bottom have the same degree. So it's like they're both approaching an infinity that's of the same magnitude. Okay, and so it turns out to be just y equaling some number other than 0. If the degree is bigger on the top, you will not have a horizontal asymptote, because in that case, if you wind up having something with a degree bigger on top, then you got an x left over up there on top. Okay, and if you think about that, then the numerator is getting much bigger as compared to the denominator. So this is going to approach this particular one is going to approach a negative infinity, but you'll get either a negative or positive infinity depending upon the other parts of the problem. Okay, like the fact this was negative here is what caused you to get a negative infinity. All right, so let's use the shortcut on these. Now, technically, these are really not what you would call a normal rational function, because 5x to the 3 halves is not a polynomial. It's really a radical. It's really a square root of x to the third power on top. But you can still use the shortcuts here to analyze what the limit would be. And so I'd like to go ahead and just do it that way. Okay. So in practice, you can really do this by just thinking about how on this one, the degree on top is 3 halves, the degree on the bottom is a 2. So it's bigger on the bottom, bigger degree on the bottom. So that means the function on the bottom is growing more rapidly than the one on top. This one is going to wind up having a limit. As x approaches infinity, the limit would wind up being 0. It's going to turn out to be that there would be a horizontal asymptote. The horizontal asymptote would be the line y equals 0. Okay. Now, technically, the more formal approach involved dividing by the x to the second that you see in that denominator. Oh yeah, I could do that here, and then divide by x to the second in the denominator everywhere. And then I could simplify that And I'd wind up here. Remember how you can subtract exponents if they're like this? So see how that's a 1.5 on top and a 2 on the bottom? So what you've really got there is a 5 over x to the 1/2 power on top. Here we have a 4, and here we have a 1 over x squared. If we put in an infinity in here, then this right here is going to 0, and so is that, and we wind up having 0 over 4, which is 0. So that's the more official way of doing it, but I'd like to be able to keep this short and sweet, and there's a lot of, it's very meaningful to understand that the leading terms are what really matter, because that little +1 doesn't really affect things when you're plugging in something like an infinity. So you can really just focus on those leading terms and realize that the degree is bigger on the bottom. Okay? Or if you wanted to do some canceling, you could look at those two terms and simplify that, right? And when you do you see how that is going to leave you with an x to the 1/2 in the bottom? And that's why that would wind up, I need a limit in there, that's why that would wind up equaling 0. Okay, so let's just use the shortcut. Bigger degree on the bottom, I know the limit's going to be 0. I know it's going to have a horizontal asymptote of y equals 0. Here the degrees are the same. That little 1 doesn't really affect anything when I'm plugging in infinities. It's so small. So when I'm looking at that, I'm just thinking about how the degree's the same top and bottom, so I know this limit is going to be equal to the ratio of the leading coefficients. I would have a horizontal asymptote at 5/4. Okay. This guy, this one is equal to, down in the denominator there, I really have 4x to the 1/2 power plus 1, in the numerator 5x to the 3/2, bigger on top. Okay, that means there's going to be no horizontal asymptote. It's going to approach an infinity of some sort. Spelled that wrong. It's going to approach an infinity of some sort. Let's think of which one it would be. Since this is positive infinity, okay, then it's going to, and this is positive and this is positive, it's going to wind up being a positive infinity there. Okay. Now, again, I could go through the lengthier process. I'm happy for you to do that. But you can really just focus on those leading terms to help you. And see, like that 5x to the 3/2 over 4x to the 1/2, just that plus 1 has so little effect we can just ignore it. That winds up being the same. If I subtracted exponents, I'd have 5x on that one. Subtract 1/2, I'd just have an x. And down here, I'd have a 4. And if I put an infinity in there, see how this is positive, and then in here is going a positive infinity? That's what you can think about to get that positive infinity. And just a side note on that, they had to have x be approaching a positive infinity. So what if x were approaching a negative infinity? Okay. Do you see how that would be a problem on this one? Because down in that denominator and even in the numerator, that's really like having a square root of x cubed. Down here we have a 4 square root of x plus 1. If this were negative, we wouldn't even have a real number. Okay, it wouldn't even have existed because of the square root of a negative. Okay. All right. Now, it can get a little more complicated. I think I'm going to stop again and do the next one.